Colorado Territory, 1885. While his neighbors rushed to build standard log cabins before winter, Caleb Frye was doing something that made no sense to anyone watching. He was burning his own house, systematically charring every exterior plank and log face with a long-handled torch until his entire 16 by 20-foot cabin turned black as coal. They called it wasteful, called him a fool, said he'd ruined $40 worth of good lumber, nearly 2 weeks' wages for a working miner. Harlan Pike, the local carpenter, warned everyone that charred wood would crack, flake off, and turn the cabin into an oven come summer. But Caleb had seen something in Japanese coastal ports that nobody else understood. Houses clad entirely in charred black boards that outlasted everything around them. Then January arrived with a vengeance. 10 straight days of sub-zero cold, nights hitting 20 below, days that barely reached zero. Standard log cabins froze families to the bone, burning through half their winter wood just trying to stay alive. Ice formed 3 feet from their fireplaces. But that black cabin, on the same fuel, it ran 15 degrees warmer than every natural log cabin around it. While neighbors shivered at 39 degrees inside, Caleb worked comfortably at 54 degrees. What did he understand about heat, sun, and survival that an entire frontier community had missed? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. The Pacific wind carried salt spray across the Yokohama docks as Caleb Frye watched something that would save his life 7 years later in the Colorado Rockies. A Japanese carpenter was methodically charring cedar planks with controlled flame, turning pristine white wood into blackened boards that looked ruined to Western eyes. The locals called it yakisugi, though Caleb never learned the name. He only saw that the charred siding on the harborside warehouses had weathered decades of storms while newer, untreated buildings rotted and warped in the coastal humidity. Caleb was 26 then, working the merchant routes between San Francisco and Asian ports. He had the kind of restless intelligence that noticed details other sailors missed, how certain buildings lasted while others failed, which techniques worked and which were just tradition. The charred wood stuck in his memory, not because it looked impressive, but because it clearly worked. Those blackened boards shed water like iron, resisted the insects that devoured raw timber, and stood solid while painted structures around them peeled and sagged. By 1884, Caleb had saved enough to file a homestead claim in Colorado Territory near a booming mining camp at 9,000 feet elevation. The altitude meant brutal winters and intense summer sun, conditions that sorted working methods from wishful thinking in a single season. He selected a 160-acre plot with southern exposure, thinking already about the sun's path and the shelter the ridgeline would provide from northern winds. His cabin site sat on a gentle slope facing southeast, positioned to catch the first light of dawn and hold it through the afternoon. While his neighbors chose their building spots for convenience, close to the wagon road, near existing clearings, or simply wherever the first good trees stood, Caleb studied the sun's arc through the seasons and placed his foundation accordingly. The decision would prove critical, though he couldn't yet quantify why. Spring brought the serious work of construction. Caleb laid out a 16 by 20-foot foundation, standard size for a bachelor homesteader, with walls that would rise 8.5 feet to the plate. He selected pine and spruce logs averaging 9 to 10 inches in diameter, seasoned but still heavy with sap. The logs went up in traditional saddle notch style, each course fitted tight against the one below, gaps chinked with clay and moss mixed with animal hair for binding. But as the walls rose, Caleb began implementing modifications that made his neighbors shake their heads. Instead of orienting the cabin for road access like everyone else, he positioned the long wall directly south, maximizing the surface area that would face the winter sun. He cut most of his windows into that south wall, leaving the north side nearly solid except for a single small opening. Inside, he built a low knee wall of fieldstone along the southern interior, creating thermal mass that could absorb and re-radiate heat, though he thought of it simply as a convenient place to stack tools and supplies. The real controversy began in late summer when Caleb started his charring operation. Working in 10-foot sections, he leaned boards against a rough stone trench he'd built specifically for controlled burning. Using a torch made from pitch-soaked pine, he brought each surface to a deep alligator skin char, about 1/8 inch thick. The process required careful attention. Too little flame left the wood only scorched. Too much burned through into the structural timber beneath. Each wall section took 3 to 5 minutes of steady flame application. Caleb kept notes in a small leather journal, recording how the surface temperature climbed from roughly 140 degrees Fahrenheit on raw wood to over 400 degrees during active charring before he doused each section. The charred layer formed a protective carbonized skin that would resist moisture, insects, and rot far better than bare wood based on what he'd observed in Japan. The community reaction was immediate and harsh. Riders passing by saw black smoke and a man apparently destroying his own building materials. They dubbed him Cinder Cabin Caleb and calculated that he was ruining $40 to $60 worth of good boards, a meaningful loss when a cash miner might earn $3 to $4 a day in good conditions. Harlan Pike, who had carpentry experience from Missouri, publicly warned that charred wood would flake off within a year, crack from thermal expansion, and create fire danger rather than prevent it. The local authority figure, Elias Turner, carried weight as the man who ran the sawmill and had built several of the more substantial structures in camp. Turner drew on conventional wisdom from carpentry manuals and railroad construction standards, which uniformly recommended light-colored natural wood siding. He advised neighbors not to copy Caleb's methods, predicting that the black surface would trap heat dangerously in summer and provide no benefit in winter beyond what proper chinking and sufficient firewood could achieve. But Caleb had already begun to notice something the critics missed. On a chilly September morning with outside air around 40 degrees, he discovered by simple touch that his south wall surface ran 15 to 20 degrees hotter than Harlan Pike's neighboring pale log wall when the sun struck it. He confirmed the difference with a basic alcohol thermometer, taking readings at midday on both surfaces. The principle was elementary: black absorbed solar radiation while light surfaces reflected it, but the practical implications were just beginning to unfold. As autumn progressed and the first light snows dusted the high country, Caleb continued his temperature observations. His journal entries recorded not just daily weather, but the performance characteristics of his modified cabin design. On clear days, even with outside temperatures in the 20s, his south wall would warm enough to create noticeable heat gain inside the structure. The charred surface was functioning as a crude solar collector, capturing energy that his neighbor's pale walls simply bounced back to the sky. The mockery continued through the fall months as neighbors stockpiled their winter wood supplies. Most families laid in 8 to 12 cords, depending on their heating setup and past experience. Caleb had cut and stacked only 6 cords, a decision that brought fresh criticism from men who viewed adequate wood supply as the cornerstone of winter survival. They interpreted his lighter wood pile as either laziness or dangerous overconfidence, not understanding that he was counting on his cabin design to reduce fuel requirements. By December, with serious cold settling over the high country, the stage was set for a practical test that would validate or destroy Caleb's reputation in the camp. His black cabin represented a fusion of Japanese charring techniques, careful solar orientation, and strategic thermal mass, methods that had evolved separately across different cultures but shared the same underlying physics. The coming winter would demonstrate whether cross-cultural building wisdom could outperform local convention measured in the most basic terms: interior temperature and firewood consumption during the months when survival depended on both. The winter that descended on Colorado's high country in 1884 proved to be one that would test every assumption about frontier survival. Historical records from similar elevations show that mining camps regularly endured average January highs in the mid-20s and lows near zero, with extreme cold snaps driving temperatures toward 30 below. At 9,000 feet, the thin air meant that clear days delivered solar radiation 40 to 50% more intense than at sea level, while the nights radiated heat back to space with merciless efficiency. Caleb's neighbors had built their cabins according to established frontier practice, following patterns that had worked adequately in lower, more forested regions. Most were oriented for convenience rather than solar gain, with doors facing the wagon road and windows placed wherever framing allowed. Their natural log exteriors displayed the pale sapwood and darker heartwood that marked properly seasoned timber, surfaces that reflected rather than absorbed the intense mountain sunlight. Chinking consisted of clay and straw mixtures, sometimes reinforced with animal hair, packed 1 to 2 inches deep into the gaps between logs. The conventional wisdom emphasized brute force heating, large fireplaces or multiple small stoves, fed by massive wood piles that represented months of summer cutting and hauling. Harlan Pike had laid in 12 cords of mixed pine and fir, calculating that he needed roughly 1 cord per month to maintain livable temperatures through the worst weather. His cabin followed standard 14 by 16-foot dimensions with 8-foot wall height, chinked with traditional clay mixture, and heated by a central box stove supplemented by a small fireplace for cooking. Caleb's approach differed in ways that seemed subtle but would prove crucial under stress. Beyond the controversial charred exterior, he had positioned his cabin to maximize solar exposure during the low-angle winter months. The long axis ran east-west with most windows concentrated on the south face, creating maximum surface area to intercept the sun's rays. Inside, his fieldstone knee wall along the southern interior provided thermal mass totaling nearly 2,000 pounds of rock that could absorb radiant heat during sunny periods and re-radiate it slowly as temperatures dropped. The physics involved were straightforward enough that any practical man could grasp them, though few had considered their implications for cabin heating. Winter solar radiation at high altitude could easily reach 500 to 700 watts per square meter on clear days. A pale wood surface might absorb 60% of that energy, while a properly charred carbon-rich surface could approach 95% absorption, nearly the performance of a perfect black body. On Caleb's 160-square-foot south wall, that difference translated to roughly 2,500 extra watts of heat input during peak sun hours, equivalent to running a small additional stove for several hours without burning any wood. The first serious test came in early November when a storm dropped 2 feet of snow overnight and ushered in a stretch of single-digit daytime highs. Standard heating patterns quickly established themselves across the camp. Families with large fireplaces found themselves burning through nearly a cord per week, fighting the inherent inefficiency of open flames that sent most heat up the chimney. Those with smaller enclosed stoves achieved better fuel economy, but still required constant feeding to maintain interior temperatures above freezing. Caleb began documenting the performance comparison systematically. His morning routine included temperature readings taken before sunrise, when solar gain played no role and heating depended entirely on retained warmth from the previous day's fire and any residual heat stored in his stone mass. Even under these conditions, his cabin consistently held 2 to 3 degrees warmer than neighboring structures of similar size and construction. The real divergence appeared during daylight hours on clear days. Around 9:30 in the morning, when the sun cleared the eastern ridge and struck Caleb's charred south wall, interior temperatures began climbing even before he added fresh wood to his stove. By early afternoon, with the stove barely ticking over on banked coals, his thermometer regularly showed readings in the low 50s, while neighbors running their heating systems harder struggled to reach the low 40s. The mechanism was visible to anyone who cared to observe it. Caleb's blackened wall surface would reach temperatures in the 70s and 80s under direct sunlight, warm enough that a man could barely keep his hand pressed against it. The logs conducted that heat inward, while the interior stone mass absorbed and stored it for gradual release. Raw wood surfaces on neighboring cabins, reflecting most of the solar energy back to space, remained only 10 to 15 degrees above air temperature, even under the same intense mountain sun. Word of these temperature differences spread through the small community, though initial reactions ranged from skepticism to outright disbelief. Harlan Pike suggested that Caleb must have superior chinking or tighter log joints, crediting anything except the charred surface treatment. Others proposed that his cabin sat in a more sheltered microclimate, or that his thermometer readings were somehow inaccurate. Elias Turner, the sawmill operator whose opinions carried weight in matters of construction, offered a more technical criticism. He argued that even if the black surface did absorb more solar energy, the effect would reverse during summer months, creating unbearable heat that would make the cabin uninhabitable. Turner's objection reflected standard building practice in temperate regions, where light-colored surfaces were preferred, specifically to avoid solar heat gain during warm weather. But Turner's analysis overlooked the seasonal dynamics of high-altitude solar geometry. The intense winter sun, tracking low across the southern sky, struck the south wall at nearly perpendicular angles during the coldest months. Summer sun, climbing high overhead, would hit the same wall at shallow angles while striking the roof and north-facing surfaces more directly. The charred treatment was positioned to capture winter heat when it was desperately needed, while avoiding excessive summer gain when it would be unwelcome. As December brought more consistent cold and the first sustained below-zero nights, fuel consumption patterns began to diverge noticeably. Families relying entirely on wood heating found themselves burning through their stockpiles faster than anticipated. Some had already consumed nearly half their winter supply by Christmas, facing the grim prospect of rationing fuel during the coldest months still ahead. Others began ranging further from camp to cut additional wood, a dangerous undertaking in deep snow and extreme cold. Caleb's fuel usage told a different story. His daily journal entries recorded steady but modest wood consumption, typically 2 to 3 splits of seasoned pine or fir per day during cold spells. On sunny days, he could often let his stove burn down to coals by mid-morning and still maintain comfortable interior temperatures through the afternoon. His projected consumption pointed toward completing the winter on 5 to 6 cords total, nearly half the amount his neighbors were burning. The community was beginning to confront an uncomfortable reality. The man they had mocked for burning his lumber had created a cabin that demonstrably outperformed conventional construction in the specific conditions where performance mattered most. As January approached with its promise of the season's most brutal cold, even the skeptics were paying attention to the temperature readings coming from the black cabin and wondering what they might have missed about the relationship between color, sunlight, and survival on the winter frontier. The Arctic outbreak that settled over the central Rockies on January 12th arrived without the usual warning signs that experienced frontiersmen had learned to read. No gradual temperature drop or shifting wind patterns preceded the polar air mass that swept down from Canada, bringing with it the kind of cold that could kill a man in minutes and freeze solid anything not actively heated. Within 6 hours, daytime temperatures plummeted from the teens to below zero, and they stayed there for the next 14 days. By the third night, mercury thermometers throughout the mining camp had retreated into their bulbs, registering only that the air had dropped below their lowest calibration mark of 20 below. Men who ventured outside reported that spit froze before hitting the ground, and exposed skin began numbing within 30 seconds. Wind chills drove the effective temperature into territory that made simple survival the primary concern of every household. Harlan Pike's natural log cabin, built according to specifications that had served adequately in Missouri winters, began failing in ways that revealed the inadequacy of conventional methods under extreme stress. By dawn of the fourth day, with outside temperatures holding steady at 22 below, the interior of his cabin had dropped to 28 degrees despite running his box stove continuously through the night. Ice formed on the interior walls within 3 feet of the fire, and the water bucket beside his bed froze solid. The logs themselves contributed to the problem in ways that Pike had never anticipated. As temperatures plunged, the wood contracted at different rates depending on species, grain orientation, and moisture content. Gaps opened between courses despite careful original chinking, creating hairline cracks that allowed frigid air to infiltrate. The clay and moss mixture, brittle in extreme cold, fell out in frozen chips, leaving dozens of quarter-inch openings that functioned as refrigeration vents, drawing warmth from the interior. Pike's fuel consumption accelerated beyond any sustainable rate. His 12-cord woodpile, carefully calculated for a normal winter, began disappearing at nearly half a cord every 3 days as he desperately fed both his stove and a hastily rekindled fireplace. The fireplace, with its massive stone chimney, proved particularly wasteful, sending most of its heat directly up the flue while drawing cold air into the cabin through every available crack and gap. Other families faced similar crises with variations that depended on their heating methods and construction details. The Kellys, relying on a large stone fireplace for both heating and cooking, watched their woodpile shrink at the alarming rate of one full cord per week. Their children slept in layers of every available blanket, while parents took shifts through the night feeding the fire to prevent complete interior freezing. Sarah Kelly later recorded in her diary that even with the fire burning continuously, frost formed on interior walls more than 6 feet from the hearth. Livestock shelters, built with even lighter construction than human habitations, became death traps for animals whose owners had considered them adequate protection. Barns constructed of inch-thick boards with no thermal mass or insulation dropped to within 5 degrees of outside air temperature. Cattle and horses, confined in structures that offered little more protection than a windbreak, began showing signs of severe cold stress despite thick winter coats and supplemental feeding. In stark contrast, Caleb's charred cabin maintained performance that seemed to defy the brutal conditions surrounding it. His morning temperature readings, taken at dawn before any solar contribution, consistently showed interior temperatures between 34 and 36 degrees when outside air registered 20 below, or worse. While still bitter cold by normal standards, this represented a temperature advantage of 8 to 10 degrees over his neighbors' cabins before the sun even appeared. The true divergence emerged during daylight hours on the few clear days that punctuated the cold snap. Around 10 o'clock, when the low winter sun finally cleared the eastern ridge and struck Caleb's blackened south wall, interior temperatures began climbing despite minimal additional fuel input. The charred surface, absorbing nearly all incident solar radiation, quickly heated to temperatures approaching 100 degrees, even with outside air at 5 below zero. The thermal mass system that Caleb had built into his cabin's interior proved its worth during these extreme conditions. The fieldstone knee wall and additional rocks placed behind his stove absorbed radiant heat during the brief sunny periods and released it gradually as the sun declined. This stored energy provided measurable heating benefit well into the evening hours, extending the warmth captured during peak solar periods throughout the night. By early afternoon on clear days, with his stove running at minimum output on banked coals, Caleb's thermometer regularly showed 54 degrees, while Pike's cabin, with a stove burning actively, struggled to reach 39 degrees. The 15-degree difference represented the measurable advantage of solar collection and thermal storage over brute force wood burning, demonstrated under conditions where both systems were operating at their limits. The wood consumption differential became impossible to ignore as the cold snap extended into its second week. Pike had already burned through nearly 6 cords of his winter supply, facing the prospect of cutting and hauling additional wood in sub-zero conditions or rationing fuel during the coldest period anyone could remember. Other families reported similar consumption rates that pointed toward complete exhaustion of their wood supplies before winter's end. Caleb's consumption pattern remained remarkably consistent despite the extreme conditions. His journal recorded daily fuel use averaging 3 to 4 splits of seasoned wood, with additional consumption only on overcast days when solar gain contributed nothing to interior heating. His projected total for the entire cold snap was less than 1 cord, including the fuel needed for cooking and maintaining basic comfort during the worst weather of the winter. The community response shifted from mockery to grudging attention as the temperature differential became undeniable. Pike, despite his earlier skepticism, began asking specific questions about cabin orientation and wall treatment. The Kellys, facing potential fuel exhaustion, requested permission to shelter in Caleb's cabin during the coldest nights, discovering firsthand that the interior remained comfortable enough for normal activities while their own home had become barely habitable. The crisis revealed fundamental limitations in conventional frontier building methods when subjected to extreme but not unprecedented weather conditions. Standard log construction, adequate for moderate cold, failed catastrophically when outside temperatures dropped into ranges that occurred regularly in high-altitude regions. The difference between survival and comfort often came down to design decisions made months earlier when the consequences of poor thermal performance seemed merely theoretical rather than life-threatening. As the cold snap finally began to moderate after 2 weeks of punishment, the mining camp's residents faced a new reality. The man whose building methods they had dismissed as wasteful foolishness had demonstrated superior performance in measurable terms that no one could argue with. The black cabin had not only survived the worst weather in memory, but had done so while consuming half the fuel of conventional construction, providing its occupant with living conditions that bordered on comfortable when others barely achieved survival. Thomas Brackett arrived at the mining camp in late January, with the practical skepticism of a man who had spent 15 years measuring temperatures in mine shafts, boiler rooms, and smelting operations across the Western Territories. As a consulting engineer for several mining companies, he carried precision instruments and maintained detailed logbooks of thermal performance in industrial settings. Word of the mysteriously warm black cabin had reached him through mining camp gossip, but Brackett approached such claims with the methodical doubt of someone who trusted numbers over stories. The engineer brought with him a calibrated alcohol thermometer accurate to within 1 degree, along with a blackened bulb radiometer of the type used in mine ventilation studies to measure radiant heat transfer. These instruments represented the cutting edge of practical temperature measurement for field conditions, far more precise than the basic thermometers most settlers relied upon. Brackett had used similar equipment to optimize heating systems in mine offices and worker housing, where fuel economy directly affected operating costs. On February 3rd, with outside conditions stabilized at 10 degrees and clear skies providing optimal solar exposure, Brackett proposed a controlled comparison that would settle the question of the black cabin's performance once and for all. He insisted on identical fuel loads, synchronized timing, and multiple measurement points to eliminate variables that might skew results. Both Caleb and Harlan Pike agreed to participate, each confident that the test would vindicate his approach to frontier construction. The experimental protocol was straightforward enough that any practical man could follow and verify the results. Each cabin would burn exactly 10 pounds of seasoned pine splits, selected from the same tree and split to similar dimensions. The wood would be loaded at the same time and allowed to burn under normal draft conditions. Temperature readings would be taken at 30-minute intervals for 4 hours, measuring both interior air temperature and exterior wall surface temperatures on the south-facing sides. Brackett established his measurement stations with the precision of a man accustomed to industrial standards. Interior thermometers were positioned 4 feet above the floor and 6 feet from the heating source in each cabin, locations that would represent typical living space conditions rather than hotspots near stoves or cold zones near walls. Exterior measurements would be taken at chest height on the center of each south wall, where solar exposure would be most direct and consistent. The surface temperature readings revealed the fundamental mechanism behind Caleb's heating advantage with stark clarity. Within 1 hour of direct sun exposure, the charred exterior of Caleb's cabin registered 87 degrees, while Pike's natural log wall reached only 59 degrees under identical conditions. The 28-degree difference represented the measurable impact of surface color on solar absorption, a principle that Brackett could explain in practical terms any working man would grasp. Brackett sketched the basic physics on a scrap of pine board, avoiding mathematical formulas in favor of workshop logic that resonated with men who understood tools and materials. The black surface acted like a blacksmith's forge, he explained, soaking up the sun's heat and conducting it inward through the log structure. The pale wood behaved more like a mirror, bouncing most of the available energy back toward the sky where it provided no heating benefit whatsoever. The interior temperature measurements documented the cumulative effect of this solar collection advantage over the 4-hour test period. Starting from identical baseline temperatures of 38 degrees in both cabins, the readings diverged steadily as the sun climbed higher and solar gain became more significant. After 2 hours, Caleb's cabin had reached 48 degrees, while Pike's remained at 41 degrees, a 7-degree gap that continued widening through the afternoon. By the end of the 4-hour measurement period, the temperature differential had stabilized at 15 degrees, with Caleb's interior reading 52 degrees compared to Pike's 37 degrees. Both cabins had burned their 10-pound fuel loads completely, eliminating wood consumption as a variable in the performance comparison. The advantage came entirely from solar collection and thermal storage, representing free heat that required no additional labor or materials beyond the initial charring treatment. Brackett calculated the energy equivalent of this solar gain using rough estimates based on his experience with industrial heating systems. The extra heat collected by the charred wall, surfaced during peak sun hours, was roughly equivalent to burning an additional 20 to 30 pounds of wood per day during clear weather. Over the course of a full winter season, this solar contribution could easily represent 2 to 3 cords worth of heating value delivered without cutting, splitting, hauling, or storing any additional fuel. The implications extended beyond simple fuel economy to questions of safety and reliability during extreme weather events. Brackett had observed how quickly wood supplies could be exhausted during severe cold snaps, leaving families vulnerable when hauling additional fuel became dangerous or impossible. A heating system that reduced baseline fuel consumption by 30 to 40% provided a crucial margin of safety when survival depended on making limited supplies last through unpredictable weather. Word of the controlled test results spread quickly through the mining camp, carrying the authority of precise measurement and professional validation. Brackett's reputation as a practical engineer who dealt in measurable facts rather than theories lent credibility to findings that might otherwise have been dismissed as coincidence or exaggeration. The 15-degree interior temperature advantage, an equivalent of several cords worth of free solar heating, became accepted facts rather than disputed claims. The engineer connected these results to broader patterns he had observed in his work across different climatic regions. Indigenous building traditions and older European practices often incorporated dark surfaces, thermal mass, and solar orientation in ways that improved heating efficiency, though the principles were rarely explained in modern technical terms. The knowledge existed in practical form among builders who had learned through direct experience rather than formal engineering education. Harlan Pike, confronted with undeniable measurement data, began asking detailed questions about charring techniques and cabin orientation. His initial resistance gave way to practical interest as he calculated the potential wood savings and improved comfort that solar collection could provide. Other families, having witnessed the controlled demonstration, started planning modifications to their own cabins that could capture at least some of the heating benefits Caleb had achieved. The validation process transformed community perception of experimental building methods from suspicious novelty to proven technique worthy of adoption. Brackett's documentation provided the technical credibility that allowed practical men to overcome their conservative building habits and consider approaches that departed from conventional frontier practice. The black cabin was no longer an eccentric experiment, but a demonstrably superior solution to the fundamental challenge of heating efficiency in extreme climates. By early March, as winter began its gradual retreat and residents assessed the damage to their fuel supplies and heating systems, the measured performance advantage of solar collection and thermal storage had established a new standard for high-altitude construction. The man who had been mocked for burning his lumber had proven that cross-cultural building wisdom, validated by precise measurement, could outperform local convention in measurable terms that translated directly to survival and comfort on the unforgiving frontier. Spring brought validation in the form of practical adoption, rather than theoretical argument. As snow melted from the high country and residents tallied their winter fuel consumption, the measurable advantages of Caleb's methods could no longer be dismissed as temporary luck or measurement error. Families who had burned through 10 to 12 cords of wood during the brutal winter began seeking specific advice about charring techniques, cabin orientation, and thermal mass placement. The conversation had shifted from whether the black cabin worked to how its principles could be replicated. Caleb approached requests for assistance with the same methodical precision he had used in his original construction. He demonstrated the charring process in controlled sections, showing how to achieve the optimal 1/8-inch carbonized layer without burning through to structural timber. The technique required steady attention and proper timing, 3 to 5 minutes of flame exposure per section, maintaining surface temperatures between 300 and 400 degrees before quenching. Too shallow a char provided minimal weather protection, while excessive burning weakened the wood's structural integrity. The first successful adoptions came from practical necessity rather than theoretical conviction. The Kelly family, having exhausted nearly their entire wood supply during January's cold snap, requested help charring the south wall of their existing cabin. Working in 10-foot sections over 3 days in late March, Caleb supervised the controlled burning of their exterior logs. creating a blackened surface that immediately began collecting solar heat during clear spring days. The results appeared within the first week of treatment. Interior temperatures in the Kelly cabin rose 5 to 8 degrees above previous baselines during sunny periods, even with minimal wood burning. Sarah Kelly documented the change in her diary, noting that the cabin felt noticeably warmer by mid-morning and retained heat longer into the evening. The family began planning a complete reorientation of their living space, moving beds and work areas to take advantage of the improved thermal performance along the treated wall. Harlan Pike's conversion represented a more comprehensive adoption of the integrated approach. Rather than simply charring existing surfaces, Pike decided to relocate his cabin entirely, positioning the new structure to maximize southern exposure while incorporating thermal mass elements he had observed in Caleb's design. The new 16 by 20-foot cabin featured a south-facing long wall with most windows concentrated on that exposure, along with a fieldstone interior wall that could absorb and re-radiate solar heat. Pike's construction process became an informal teaching laboratory where other settlers could observe proper implementation techniques. Caleb provided guidance on log selection, foundation orientation, and the specific charring methods that had proven effective during the previous winter. The collaborative approach helped establish standardized procedures that could be replicated reliably, reducing the experimentation and potential errors that might discourage other adopters. By summer's end, 6 cabins in the immediate area had received some form of solar heating modification, ranging from partial wall charring to complete reconstruction incorporating orientation and thermal mass principles. The modifications represented a significant investment of labor and materials, but families who had struggled through the previous winter were motivated by the prospect of improved comfort and reduced fuel requirements during future cold seasons. The performance data from these early adopters validated the broader applicability of Caleb's methods beyond his specific site conditions. Families who implemented both charred south walls and strategic thermal mass reported interior temperature improvements of 10 to 15 degrees during clear winter days, along with fuel consumption reductions averaging 30 to 40%. These consistent results across different cabin sizes and construction details demonstrated that the underlying principles worked reliably when properly applied. Documentation of the spreading adoption reached beyond the immediate mining camp through the practical networks that connected frontier communities. Thomas Brackett included a detailed account of the charred cabin heating system in a technical report to mining company executives, describing the measured performance advantages and potential applications for worker housing in remote locations. His professional endorsement carried the methods into broader engineering discussions about efficient heating in extreme climates. The local newspaper, serving mining camps throughout the region, published a straightforward account titled "The Black Cabin That Burns Less Wood," including basic construction specifications and performance figures. The article avoided theoretical explanations in favor of practical details that working men could understand and implement. Cabin dimensions, wall treatment procedures, fuel consumption comparisons, and temperature measurements taken during controlled tests. Regional diffusion occurred through the informal knowledge networks that connected mining camps, trading posts, and supply routes across the territory. Teamsters and traveling merchants carried accounts of the heating innovation to other high-altitude communities, where similar climate challenges made the technique immediately relevant. By 1887, variations of the charred wall solar heating system had appeared in mining camps across Colorado and into Wyoming territory. The broader technical community began recognizing connections between Caleb's practical innovations and established principles of heat transfer and building performance. Engineers working on industrial heating problems noted similarities to furnace design principles, where dark surfaces and thermal mass were routinely used to improve efficiency. Architects familiar with European building traditions identified parallels to Mediterranean practices that used dark stone and strategic orientation to manage thermal loads. Modern recognition of the same principles came full circle as 20th century sustainable building movements rediscovered traditional techniques that had been temporarily displaced by cheap fossil fuels and mechanical heating systems. Passive solar design, thermal mass heating, and charred wood cladding emerged as components of energy-efficient construction, validating through contemporary research the same physical principles that Caleb had applied through cross-cultural observation and practical experimentation. The charred wood technique itself experienced a renaissance as architects and builders sought durable, chemical-free exterior treatments that could provide both weather protection and aesthetic appeal. The Japanese yakisugi method that had originally inspired Caleb's innovation found new applications in contemporary construction, where environmental concerns and energy efficiency made traditional techniques newly relevant for modern builders. The fundamental lesson transcended specific construction details to address broader questions about innovation and knowledge transfer in frontier communities. The most effective heating solutions emerged not from local convention or imported theories, but from the practical synthesis of techniques that had proven successful under similar conditions in different cultures. The man who lived most comfortably through the worst winter was the one who trusted empirical observation over community consensus, validating old methods through new applications rather than dismissing them as primitive or irrelevant. On the frontier, survival often depended on recognizing that the hardest working solution was not necessarily the best solution, and that comfort and efficiency could be achieved through design rather than pure labor. The black cabin stood as enduring proof that when winter tested every assumption about shelter and fuel and warmth, the families who endured best were those who had let the sun do half the work before the cold ever arrived.